Okay, it's now 9 o'clock, and welcome everyone to our Innovation Week plus Innovation Quarter lecture on human artificial intelligence and robot teaming. And so glad that you could all make it. I'm Nancy Cooke, and I will be doing this presentation with Dr. Robert Gutzwiller, we're both in human systems engineering. And I'm the director and he's the associate director of the Center for Human Artificial Intelligence and Robot Teaming under the Global Security Initiative at ASU. So we welcome you. We're going to be doing several things today. We will have an introduction to our center and to the topic of human AI robot teaming, and then introduce you to one specific project that we're doing, show you a little bit of a video of that project in action, and then have some Q&A. I want to take this time though to ask you to put questions in the chat, and we have Pauline Jewett online who can be monitoring that chat channel. We want this to be interactive. It's a little bit hard on Zoom with so many people, but we welcome your questions and we'll get you answers even if it's later in the day. We'll present a second project after the Q&A and have some more Q&A, and then Dr. Gutzwiller will present integrating humans and machine learning. So without further ado, let me get started. I wanted to tell you just a little bit about the unit at Arizona State University that both Dr. Gutzwiller and I come from. It's Human Systems Engineering. I consider human systems engineering to be the perfect marriage between engineering and psychology. We make technology work for people. We design technology tools, systems, environments, and even societal organizations and processes to work for people. And that's what we're all about. And we, Dr. Gutzwiller and I, and others also on the line, are not only in human systems engineering, but we are also part of the Center for Human Artificial Intelligence and Robot Teaming. That's a center at ASU that's made up of lots of different faculty affiliates and their graduate students. We believe that the coordination of teams composed of multiple humans and synthetic agents is very important for very many domains: transportation, military operations, space exploration, industry, and medicine. So these human AI robot teams are increasing, and we think it's important to study them. We have at least 60 affiliated faculty across these various disciplines, and I think it's very important to make it clear that putting humans and AI and robots together in a way that is human-centric involves lots of different disciplines, from human factors and psychology to engineering and robotics and ethics. And we team with people who are in the arts and in business and in law. So there's lots of disciplines that are needed to solve this problem. And the other thing about CHART, the Center for Human AI Robot Teaming, is that we take teaming seriously. So a lot of people throw that term around, human AI robot teaming, but they don't really take the word team seriously. So it's kind of putting these things together, you have a team. But I'm someone who's studied teams for at least 25 years. Mostly they've been all human teams. So I take this word seriously, and a team is defined in the literature as two or more teammates with heterogeneous roles and responsibilities who work interdependently toward a common goal. So you can think of a team as a system. It's a small system, but you can have larger teams. And then once you start integrating them with the technology, it becomes even more, it's bigger and a more complex system. We use the term human systems integration to talk about how you take systems and integrate the humans and the technology. And I think that's what's needed here. So let's talk about taking teaming seriously. What do we mean by a human AI robot team? Well, one thing we know about teams is that team members have different roles and responsibilities. And to me, this means that we should not replicate humans in robots or in AI. Why do we need to reproduce ourselves when we already can reproduce ourselves pretty well? And what we need is AI or robots that are complementary, that do things that we don't want to do. So lately, I've been looking at AI, or robots for that matter, which is really an embodied AI, as a different species. And been even thinking about making them team with humans like animals can team with humans. And can we take some principles, and I just got off the phone with Brian Hare from the Duke Dognition Unit, studies theory of mind in dogs, trying to figure out how we can take what we know about human-animal teaming and apply it to human-AI teaming. We also know that effective teams understand that each team member has different roles and responsibilities. And good teams avoid role confusion, but they back each other up as necessary. And we have some data in our lab that indicates that what autonomy really needs is an understanding of the whole task. And I'm using autonomy as a general term that includes robots and AI. But we need to have autonomy, understand the task as a whole, understand what other team members are doing. And when it doesn't do that, it ends up being a selfish teammate. Also, effective teams share knowledge about the team goals and the current situation. And over time, this facilitates communication and coordination. So one of the things that this suggests is that humans and robots, humans and AI should train together as a team before they're effective. And effective teams also have team members who are interdependent, and thus they need to interact and communicate even when direct communication isn't possible. So to me, this suggests that maybe we need some other communication model that differs from natural language understanding and production, which has been a pretty tough nut to crack for artificial intelligence. Maybe some sort of signaling gestures. Animals pay attention to body language. And so I think there's other ways that we can think about human-AI communication. And finally, interpersonal trust is really important to human teams. Autonomy, therefore, needs to explain and be explicable. We think this is important to increasing trust in human autonomy teams. But the challenge is that our research in human autonomy teaming, that's what that HAT stands for, can't wait until the autonomy is developed, because by then it's too late to provide meaningful input. So we can't, for instance, have somebody present us with a robot and say, how is this robot teaming with humans? Because by then it's going to be too late to make any kind of major changes in the robot. Instead, we need a research environment or test bed to get ahead of the curve and conduct research that can guide autonomy development. So next I'm going to tell you a little bit about our approach to doing research in this area before the development of the AI, before the development of the robots. I call the procedure the living lab procedure. And I think the important thing about this procedure is that it begins and ends in the real world, in the field as we call it. We do what's called cognitive task analysis in the field. We bring that into the lab and create a test bed that can then exercise in humans or in the AI the kinds of tasks and skills that people are performing, and maybe machines, in the real world. So we kind of abstract the real world into the lab, and we conduct experimentation in the real world and develop measures and models and develop theories. And then hopefully later this transitions back, what we find transitions back to the real world. So we understand, these are the steps of this process, understand the real world tasks. And we use heavy use of simulation, synthetic task environments, and another interesting technique that's called the Wizard of Oz. The Wizard of Oz paradigm uses humans to simulate robots or to simulate the AI in order to be able to enhance our impact early in robot development. So again, we don't want to wait for the AI or the robot to be fully developed, but we use Wizard of Oz to test different things in our synthetic task environment to see which kind of approach works best. We focus heavily on measurement, and in my lab, we're big on developing real-time, unobtrusive, systems-level dynamical measures and empirical models. We do human subjects experimentation. We put the humans in the test bed. We sometimes put AI in the test bed, and we want to use our measures to assess the effectiveness of the human autonomy teams across multiple criteria. And then we engage in the translation part, and that involves transdisciplinary knowledge exchange between those who are developing the autonomy and those who are conducting the human subjects research. So in general, the objectives of our research program is to develop realistic research test beds for empirical and controlled human in the loop studies, to develop and by the way, recently, as of like March of this year, we've had to pivot to making these research test beds accessible online so that we can conduct our studies remotely. We develop real-time unobtrusive systems level dynamical measures and models. We gain a theoretical understanding of what I call team cognition and its drivers for human machine teams. We use our empirical findings as guidelines for robot agent development and try to improve that human machine team performance by designing machines to be good teammates. And please contact us. We are very much interested in collaborating with all sorts of disciplines. We collaborate with many as it is now. We put on workshops and conferences and welcome people from all walks of life to participate in this really exciting research. So I want to switch now to, maybe I'll stop there. We have a few minutes. Are there any questions so far? Anything? I can't see the chat. So.
There's one that says, how can one get involved?
Yes, so I would say email me and we will talk. And you can find me pretty easily on the ASU website. Nancy Cooke, C-O-O-K-E. We have one good way to get involved is to participate in our experiments, and you'll see some examples of those coming up right now. Okay, so what I'm going to talk about now is an example of one of the projects that we're doing. This is a project that's done and sponsored by DARPA and done with a teammate Aptima. It's called ADAPT, which stands for Adaptive Distributed Allocation of Probabilistic Tasks. And I'm going to tell you a little bit about what we're doing, and then we'll show you a video of that particular experiment in action. And I want to point out, we're showing you video of not real participants doing our experiment, but of people in our lab doing the experiment for the purpose of confidentiality. Okay, so in this project, we're developing, or our teammate Aptima is developing an artificial intelligent agent that will be able to learn and adapt as it helps a team. And we're evaluating how well the AI works with a team in an urban search and rescue mission. In this task that you're going to be seeing, the goal is to save as many victims as possible. We have 3 humans in that task that are playing different roles. And they're interdependent roles. So this is an example of a good team. Everybody's doing something different. However, in this case, they're able to switch roles. So we have a hazardous materials specialist who has a shovel that can clear debris. And we have, and they operate at slow speed. And the map that you're looking at below this is the structure that's created in Minecraft that represents a collapsed office building. And they're searching for victims in this building together as a team. The second role is a search specialist who has a stretcher who can move victims and moves at a very fast speed. And then we have a medic or a medical specialist who has a medic kit who can rescue victims and moves at a medium speed. So what we're really interested in here is how these humans interact as a team and how AI can help them, can facilitate that teamwork. And what you're going to see, we do not have the AI operating, but we're still developing this test bed, and we're looking at the human interactions, their human coordination, and areas in which AI might be able to help them. So another thing to add is that their tools require renewal periodically at a cost, that there's different ways that we're thinking that they will coordinate. In this particular video, they're coordinating by audio, and it's being transcribed, in this case by Zoom. And there are several opportunities to coordinate. So what you're going to see, let me see, I'm going to go back here. What you're going to see in the video, but it just tell you now, it's about a 15-minute video, and you'll see that they have a pre-planning session. In the pre-planning session, which lasts, I think, 5 minutes, you can see that AI might suggest that they explore the space more in this part of the mission. Once the mission starts, we see that the participant whose viewpoint that we're watching is going to run out of the hammer resources. So that's a problem, and the AI might be able to support that and have an alternative strategy for exploration. You'll see also that within a few minutes, they'll start to reevaluate the plan that they came up with in the pre-planning session. Later in this mission, we have things called perturbations or roadblocks. Unexpected things happen. In this case, it's a gas leak that happens, and the team was lucky enough to be able to respond in time. You have another event that occurs where a participant forgot to pick up their markers. That's a potential form of miscommunication, and we're thinking that the artificial intelligence agent can help there. So Pauline, I believe, is going to play this video, but just watch for the coordination that happens among the team and the types of events that happen that artificial intelligence may be able to facilitate. So I'll stop my screen share. Okay.
What roles do you guys want to pick?
I'm fine starting with HMS, and could potentially go over here. Just looks like there's a lot of potential for blockages in that area.
Happy to be a specialist. Sounds like fun.
Okay. What should I be? Should I do medic or should I?
Let's maybe hold off on medic
Okay.
at the start, and then we can have the discussion if we should switch first.
Should I do an HMS then?
That sounds good. What do you think, Glenn?
Sounds good to me.
All right. Should I go with you, Dylan, to the left side, or should I do like the middle or the right side?
Yeah, maybe we should just clear that out as quickly as possible.
Okay.
That sounds good to me.
So we all just go left side first?
Sure.
Yeah.
Okay.
Is there anything else you want to talk about?
I was thinking about role switching, but we can just make that a game time decision.
Okay, yeah, you guys will run out of your tool probably before I do.
Right.
We'll see, but we'll probably make those decisions as we go.
And Glenn, are you going to focus on marking rooms or focus on transporting victims?
I'll actually pull the victims out because we're taking all that time to go through that. I just expect there to be lots of blockages in the storage area, so I might go to the cafeteria if you guys are. If I finish before you guys, I'll go to the cafeteria.
Okay.
Yeah, I think like if one of the HMS, if one of us our tool breaks, we should probably switch to medic after the tool breaks, and then the other person keeps doing HMS and just goes to the other side or something.
Yeah, see that? You want to plan on first person whose tool breaks goes to medic?
Yeah, that's fine.
Okay.
Ready to go?
Yep.
So this is the actual session. The planning just stopped.
How do you guys want to clear the rubble? Do you want to just, should we like clear all of it, or should we just do like the, I guess we could just do the lines, right?
Let's do the lines, yeah.
Okay,
I've already found one in here.
perfect.
Mark them. And Mike, I'll get started on the far side.
Okay,
Like
I'll
the
do
left
the
area.
like right side area.
Okay.
Okay, my shovel's gonna break. I'm gonna go back in. Should I just go HMS again? I think we're gonna need like both to go HMS again.
That's probably a good idea, yeah.
That is a victim, that green block. Three victims.
Should I go back to the left side, or should I start working on the right side?
Maybe come back to this left side. My hammer just broke also, so I guess it doesn't matter.
Okay.
Choose whatever.
I'll finish the left side, and then you just start going to the right side, I guess.
Okay.
Have you just not cleared like the far left?
So I went into the balcony room.
Mm-hmm.
We can make a full loop around the big hallways. I'm not sure about the two middle hallways, but yeah, I think it's just clearing stuff out of rooms at this point. Clearing rubble, that is.
Yeah.
These rooms I'm not pulling victims out of, or rubble.
Did you mark the ones with rubble?
They are being marked.
Okay.
And Glenn, it looks like maybe you were already in the middle. Did you put some markers down in there?
Yes, in the conference room.
Okay.
I think I've made my way through the left and middle side. I just need to do the right side of this section.
Yeah, I got the left side pretty much covered now. I think all the rubble's clear. I haven't checked like the insides of the rooms yet, but
I marked all the insides of the rooms rubble.
okay.
about a third of the way through.
Alright, I'm gonna move to the left side then.
You said left side. Do you mean right side?
Yeah, right side. I'm on the right side.
Okay.
Is there
I'm
anything
in
in
the
the-
first hallway.
Okay, is there anything in the middle I should clear right now?
I didn't even look. Glenn, what do you? Oh, there's a gas leak.
Alright.
Where's everybody closest to?
I'm closest to the fountain room. We'll check it right now.
Okay.
Left side, I can actually get the
Oh,
conference
I
room.
found it in the fountain room.
Okay, nice.
It's taken care of.
Is it the balcony? I said balcony.
Oh, I already got the gas leak. The 15 points was added.
That was awesome.
That was nice and quick. Yeah.
Yeah. Okay, I've cleared some rubble in the kitchen cafeteria area, and now I'm making my way to the right side. I'm gonna start on like the second hallway.
Perfect.
Okay, I finished searching all of the rooms in the left side of the building. They're all marked.
Okay.
Stretch.
What were you gonna say?
My stretcher's done, so should I change or should I keep us as search specialist?
Maybe. Dylan, do you think we've do we need a search specialist for the right side of the map? Or?
I think we might be able to get by with just using medics at this point. I've got some of the rooms marked.
Okay.
My sledgehammer did just run out with only a few blocks left to clear.
Yeah, my sledgehammer ran out too.
Should we just have one of us? I can stay as HMS if you want to switch to
Alright,
medic.
I'll switch to medic. Glenn, do you want to start triaging the left side of the map, and then I'll start the middle?
I'll start over there.
Yeah.
I'm gonna leave the victims that are out in the open and go for the victims in the rooms first.
Yeah, that's a good idea.
But there is rubble there too, so we'll still do
Oh, just direct Dylan over.
I can start out over there.
Okay. If you wanna follow me.
Yep, I'm running back down the corridor to the map.
In the meantime, I'll get a few that we're up.
What's the general area I should head?
There's a stop in the area that's kind of in the middle before you get to the left. There's
Okay.
level and a victim. So I'll actually, I don't know if that description was
Not in this white room, right? Or
yeah,
over here.
or over here. It's already been saved. Okay,
Okay.
it's good now then. The other rubble was in the middle of the sort of the conference room area.
Okay.
The hallways that go horizontal. It should be one of those rooms.
I'm gonna finish clearing the middle out, so you guys don't have to worry about like checking the middle for any victims.
Okay, perfect. Glenn, I'm not sure I'm finding the rebel.
Okay, I'll be out in a second. I can show you what I was talking about. But, well, ooh, laggy. The conference room. I'm standing in the right side of the.
Oh, I cleared some rubble in the conference room, like the middle one.
Oh yeah. Okay, great. So then that's clear.
Okay.
And maybe I think you are done here then.
Okay.
I'll make another sweep as the medic, and then I'll let you know if there's anything.
Sounds good. I will head over to the right side and
Yep, I just cleared
Finish
the
the
last
job.
victim in the middle, so it's
Great.
just the right side on the left side. Yeah, the two rooms at the end. Yeah, over in both these rooms, there's rubble that needs to be cleared.
perfect.
And then the right side, I didn't get to finish clearing yet, and there's a bunch of rubble over there.
Okay, so where the glass rooms are.
Yeah. So just once you're done with that, just go over there.
Okay. Both those rooms cleared. I didn't pick up those markers. Sorry about that.
I'll pick them up when I triage the victims.
Okay.
Oh, I just found more rubble. It is the second room on the. I don't know. I just marked it. It's the second. It's in the green hallway.
Okay.
So,
I am on my way now because I've
yeah, it's
finished
closer
the
to
rubble.
the entrance. Yeah, over here.
Okay.
It's like the second one down.
Definitely missed that my first time around. Okay.
Is there any victims in there?
There is one victim so far. There's actually two victims.
Okay, just mark it outside the door.
Okay.
Oh no, my medic kit ran out, and there's one victim in the top left corner of the left.
Well, I think we might be at a place where we can all go to medic. Do we want to do that, or do we
Yeah,
want to have?
let's do. Actually, it might be best. How many more victims do you need to save, Glenn?
I have one more.
Okay, yeah, let's keep Dylan, just stay HMS just in case if we like have missed something. Maybe just refill your shovel.
Okay, I'll do that right now.
Yeah, and then because I only have, yeah, mine's about to break on the last one, but I just have those two victims in that room. So I think I don't have time. Or should someone go the search special? Dylan, maybe you should go search specialist and just.
I think that's a good idea. Start to
Yeah.
find anybody we've missed.
Yeah.
So also noticed, I think there's like more victims on the right side. So do you think I should go to the right to help out? There's only one more on the left.
Do the one on the left first. I think I'm almost done with the right side. I think I just.
I will say if we look at the time, we're almost out, so we should try to.
Yeah, just do the left side. I'm pretty sure I only have two more on the right side, so just do the one you missed on the left side.
Okay.
I went to medic just because
Okay, yeah.
there were
that's
a
fine.
couple in the rubble.
I don't know which side you should go to. I guess whichever one. Glenn, how confident do you feel? Yeah, go to the left side. I think the right side requires less searching, so
Okay.
I think I'm done with it.
This is an example of a very good team, by the way.
Okay, I think the right side's done. Yeah. So you can just get that victim on the balcony. I think that's it.
The victim in the balcony is gone, I think.
Okay. I think that's time. But I think we got most of them.
Yeah, I think we did well.
Okay. So that was the end of the mission. As I said, that was an example of a really good team. Do we have questions? Okay, there was some discussion in the chat about what the about robots versus humans. I wanted to point out that the humans are really in the Minecraft environment and interacting with each other through their avatars. And later in our project, we'll be inserting AI into the environment, and AI will be communicating with the team to try to help the team using either those markers that you saw, colored markers that indicate there's a victim or not in the room, or using text chat. Okay, I don't see any other questions. I'm going to move on.
There's one, it says, will AI replace a team member or be an extra tool?
AI will, in this case, will not replace a team member, and it will not be doing the team task. It will just be an advisor, a facilitator of the team. You could think of the AI as a coach. And so in chart in general, we don't think of AI or robots as replacing humans, but we're trying to figure out ways that they can complement the human's task and work together with humans. Okay.
Wait, is it required more computing power or just a normal PC?
More computing power or what? More?
I think they're asking what level of computing power you need to run this sort of thing.
Okay, so for very little actually for the Minecraft testbed, we use laptops basically, and a tool called Parsec that allows people to remote into the experimenter's laptop, or we have people just join on Minecraft, which is a group game. I don't know if that's what you're asking. If you're asking about the human-robot teaming and computing power, I think the power in the human-robot teaming is really in understanding of humans and their capability and limitations, and integrating the technology well with the humans. And so it's not so much about computing power as about understanding the human strengths and weaknesses. I hope that answered the question. Okay. Are you seeing my slides again?
We are.
Okay, good. The next project that I'm going to talk about is sponsored by the Army Research Lab, and is about next generation combat vehicles. And I'll tell you what that's about. So here's the concept that hasn't been developed yet, but nonetheless, we are working on it. Again, trying to get ahead of the development of the concept and trying to understand how humans and autonomous vehicles will team in this kind of setting. So the concept is that you'll have one manned combat vehicle with these 7 people in it. One of or 2 of the people are driving the manned combat vehicle. One of them is a section leader. And we have 2 remote combat vehicles that go out ahead. Perhaps ahead of them are unmanned aerial vehicles. In the manned combat vehicle, there are 2 dyads. Each dyad is controlling a remote combat vehicle. We have developed a test bed for studying this concept. Excuse me. The test bed is due to COVID-19, one that we can access remotely. And once again, we're making use of Minecraft to develop an environment in which these manned and unmanned vehicles can operate. We use the Wizard of Oz method to simulate artificial intelligence by having one of our human experimenters act like a robotic combat vehicle. Our goal was to apply our team level metrics that we've developed to assess the team's performance to a context similar to the next generation combat vehicle context. So we have what we're calling the blue team. We have 2 remote combat vehicle operators. One's called Blue 1, the other one's called Blue 2. We have a coordinator that's called Blue 6, and we have an outside person that represents higher headquarters that's called Blue 7. There's external support in artillery, RCV repair, and updates and direction from headquarters. And so again, we're using Minecraft, Parsec, and Zoom to create an interactive task environment. This can be performed remotely by both the experimenters and the participants. So there's quite a few people involved in this particular task. We have 2 of the RCV operators. We have the RCV coordinator, and then we have experimenters playing the role of the AI or autonomy. And teams have to adapt and overcome roadblocks in this scenario to meet the mission goals. So our research question is, how do task strategies such as procedural or goal-oriented briefs before the game affect team interactions and states? So in the procedural condition, it's very rigid. The team is told what to do, who does what, told to work within a green boundary box, and they have 3 minutes to plan. In the goal-oriented condition, they also work within a bounding box and they have 3 minutes to plan, but aren't given specific rules. Oops, I just stopped screen sharing. Hold on a second. I'm going to go on and just tell you about what you're going to see in the video coming up. And again, it'll be a video, it's about 15 minutes, but like the last one, there is a time for planning. So we have we have Blue 6 as a coordinator, Blue 1 and Blue 2 are the robotic combat vehicle operators, and Blue 7 represents higher headquarters. You'll see during the mission brief, they're given some time to discuss their plan with one another, and their objectives are described. Then the robotic combat vehicle can help them by detecting objects when they may be difficult for the human to see for the operator. So that's part of the automation. They can do basically a zoom from the robotic combat vehicle to see maybe something that's far away to get closer up on it. There's also an area of operations that's bounded by a green box, and the robotic combat vehicles can notify them if they're outside the green box. So that's another way that the automation helps. During the execution of the mission, each team member can only see from their own perspective during the mission, so that this makes communication really essential for the team. You'll see that the RCV number 1 detects an enemy, and the RCV starts taking fire and warns the operator. The RCV itself lets the operator know that it has lost connection. And then the RCV2 AI detects a possible obstacle along the path. So all along, we're looking at the interactions between the AI and the robotic combat vehicle operators. The RCV2's AI misclassifies a minefield toward the end of this scenario that creates some confusion on the team. This is one of these perturbations that's intentionally designed by us into the scenario to test the team, because we have understood over the years that you can best test teamwork when you put them in situations to which they have to adapt. The operator, though, eventually gets a closer look and confirms what's actually going on, that it's not a minefield. So let me have Pauline start up the next video.
Okay, blue team, this is blue 6. We have a couple of different objectives here. Looks like our main one is to get to that friendly tank, but first we gotta check out a few things. We got a couple of key terrain and 1 enemy spotted in this general area. We also have a bit further out this K3, which looks like it's a bridge, and our task is to determine if it's passable. So how do you guys want to distribute that? Do you want to just have one of you go left, one of you go right?
Sounds good. So,
Works.
blue 6, this is blue 1. I will go C1 and check O1, K1, and K2. And then I will go to C3 to repair F1.
Copy that, blue 1. You'll go to C1, take care of the sort of northern different landmarks, and then you'll be in position to move to that F1.
Got it.
Blue 6, blue 2, I'll plan then to start north, but then head over to C2 really. And as I'm doing that, check K3 and provide overwatch for blue 1 as her RCV moves towards C3 at that point.
Roger, blue 1. So we have the split RCV 1, blue 1 rather would go north, blue 2 will go to the west for the first part of this phase. We have a second part with this repair. So you're gonna, blue 2, you're gonna be getting that overwatch and looking to the north, right?
Blue 2, affirm, and I should be able to also check obstacle 2 while doing that.
Copy that. Sounds good. I'll keep track of time if you need to know what tasks we have. If you forget, I have it in front of me. So, blue team, looks like we got 12 minutes to complete this phase. So let's get those checkpoints and then go repair that tank.
6, blue 2, moving out.
Blue 1 moving out too.
Copy that, blue team.
Blue
Blue.
6. Blue 1, I found the enemy at K1.
Blue 1, this is blue 6. The enemy at K1. Do you have cover?
Oh, I'm trying to.
Okay, copy that. I can go ahead and report that location. How about blue 2? Are you in a safe location?
Blue 2, a firm. I'm moving to top of C2 at this time.
Copy that. Blue 7, this is blue 6. We have an enemy spotted at grid V4. It's that E1.
Roger, blue 6, copy. Enemy target identified at grid V4. Over.
Blue 7 is the blue 6. Could we get some artillery at that V4 enemy?
Roger, blue 6, copy. Artillery request for enemy target at grid V4. Artillery request approved. Stand by for impact. Over.
Blue team, this is blue 6. We need both of you to observe that impact and confirm that there are no enemies after artillery impacts.
Blue 6, this is blue 1. I lost connection.
Oh, blue 1 is this is blue 6. Are you in cover still?
I'm in cover, but I lost connection. I'm south of C4.
Are you able to see the enemy still?
No, I cannot.
Oh, okay. Well, it looks like only blue 1 will be able to see that impact. Blue 7, this is blue 6. We got a connection lost at on RCV 1. They're out of bounds.
Roger, blue 6, copy. RCV1 is out of bounds. We will temporarily reconnect you and enable emergency return procedures. Have your operator remove their hands from the controls. Over.
Blue 6, blue 2, we had a good strike for the infantry. It looks like they are gone at this time.
Blue 2, thank you. I'm gonna go ahead and pass that on to you, blue 7. Blue 7, this is blue 6. We have a good impact on that artillery strike at B4.
Roger, blue 6, copy. Target destroyed at grid B4. Over.
And blue 6, blue 2, looking manually with the manual zoom in, K3 for the bridge, and it looks like it is unpassable, impassable.
Blue 2, copy that. Blue 7, this is blue 6. We have an impassable obstacle. It's that bridge at K3, grid U2.
Roger, blue 6, copy. Bridge K3 at grid U2, impassable. Over.
Blue 6, this is blue 1. I got connection, and the obstacle 1 is C-wire, which is impassable.
Blue 1, good news. Thanks for that report. Copy that. I'm going to pass that on to blue 7. Blue 7 is blue 6. We have an impassable obstacle at O1. It's actually grid B4.
Roger, blue 6, copy. Impassable obstacle at grid V4. Over.
Blue 6, blue 2, I keep getting a warning for infantry detected. When I use the auto zoom to zoom in on it, it looks like I'm getting just a minefield up where obstacle 2 should be. I'm not receiving fire, so I don't think I'm actually got a threat out there.
Okay, blue 2, that's interesting. So I guess keep your eyes on that, and I think that a minefield is probably impassable, right? So I'll probably pass that on, if that makes sense.
Blue 2 copies.
Blue 6, this is blue 1. K2 seems clear. And heading to C3.
Blue 1, copy that. Watch out for enemies to the north. You have Overwatch, so just keep that in mind. Blue 7, this is blue 6. We have obstacle O2 identified as a minefield. Do you have any input on that?
Roger, blue 6, copy. Possible minefield at O2 and grid U5. Air assets report a possible minefield in that area as well. Do not move in that area as it might damage your RCVs. Over.
Copy that, Blue 6. Blue team, that minefield is, well, dangerous and probably not move there. Definitely do not move north. Let's just focus on repairing that tank. Blue 1, have you made it to the tank?
Blue 6, Blue 1, yes.
Okay, Blue 1, I'm going to go ahead and request the repair. Please stay in position.
Roger.
Blue 7, this is Blue 6. We have RCV 1 in position for that friendly tank repair.
Roger, Blue 6. Copy. RCV 1 is in place for friendly tank repair. Tech support is linking in with that vehicle now. Stay in place for 10 seconds.
Okay, Blue 7, copy that. Blue team, please stay in place for 10 seconds.
Roger.
Blue 2 copies. And I've
Blue 6.
manual.
Blue 6, break. Blue 6, this is Blue 7. Repair friendly tank complete. You may carry on with the rest of the phase. Over.
Blue 7, copy that. Who was that, Blue 2?
Blue 6, Blue 2, just been manually checking and zooming around. I'm not seeing any threats, not receiving fire. It doesn't look like Blue 1 or RCV 1 has been getting shot at. So I think that is just triggering off of the minefield for the warning.
Blue 2, this is Blue 6, copy that. Sounds good. Are we done with our tasks?
Blue 2, I'm complete with task, and Charlie 2 at this point, C2.
Blue 6, Blue 1, I complete my task and I'm at C3.
I'm going to copy all. I'm going to go ahead and pass that final report on to Blue 7. Blue 7, this is Blue 6. Appears that we are completed each task in this phase. We're complete and in position.
Blue 6, this is Blue 7, Roger. Copy all tasks in phase 1 complete. Blue team, hold in place and await further instructions. Over.
We have a few minutes for questions, but I just want to give you a bigger picture of what we're trying to do there. We're looking at the way that the team is interacting, and the team includes the RCVs, the actual automation. And we're trying to take their interactions, we're measuring them, and then we want to be able to say something about the team's situational awareness, the team's trust, the team's adaptation and resilience, and their overall effectiveness. And so our goal here is to try to figure out how to best measure those things in this human AI team. So any questions? And I have some of the people from this team are also on the Zoom, so they can probably answer questions as well. I will also add that we're running experiments on these 2 test beds as well as others, and we welcome willing participants. And usually you get paid for participating in these experiments. And if you like Minecraft, they might even be fun. No questions? Questions about human AI robot teaming in general, or comments? Okay, to participate in our experiments, we send out various notices to listservs, but you can email me, and I'm going to put that in the chat. I may regret this, but I will send you to the right channels. We also can take volunteers to help in our lab, and these days that means sitting at home and remoting into via Zoom to one of these test beds. We also have in chart some physical test beds that we're developing and have developed, and we can provide tours, virtual tours for now, of all of those test beds if you're interested. I'm now going to turn it over to Dr. Gutzwiller, who's going to talk about machine learning and human teaming, machine learning.
Thanks, Nancy. So thanks for sticking around, everybody. We got about an hour left in the session. Let me go ahead and share my PowerPoint here. Thank you for coming. So today what I'm going to talk about is sort of this merger of machine learning and human, because what we've probably heard of a lot in the media and things like that is that we're going to use machine learning, and oftentimes when people discuss that, they think, well, we're going to replace people with it. So you've heard of these intelligent chat agents that Facebook and others were researching, and the idea was that if you learn enough about how people interact from the machine side, you really don't need people involved in that process. And what they found out after a long time and a lot of money was they were wrong. And this is something that's been happening in a lot of other domains as well. Now, it's not saying that machine learning never can replace human activity, but for things that are very complicated, and especially as you get into social stuff or you get into areas in the military where there's lots of complexity, it's very difficult to talk about replacing people. And of course, you heard from Nancy earlier about the need to create true teams. And so our perspective is that we're not trying to replace people in any of these tasks. We're trying to develop technology that facilitates what they're trying to do. And so this project in particular is going to talk about that. And so I want to start with just a quick acknowledgement. I did this work when I was a member of the civilian scientists at the Navy. And so I had some great collaborators, John Reeder and Doug Lang, who worked there. But we were also sponsored by a variety of government agencies. And of course, the views and opinions that I express here are just mine, they're not the government's. And so I want to start with this example to get you thinking about how we design and develop technology. Now, this is an art exhibit that was done by, I believe, a Danish artist. And in this art exhibit, what he's done is he's built this little wooden contraption, and it has some handles on it, and it's actually mounted on a little wheeled cart. And it has a voice box inside. And the voice box is basically talking to people who come to the art exhibit and asking them for help. So you imagine walking into this room and you see this weird box looking thing, and it says, hey, like, would you mind moving me to the other side of the room? I don't think I'm in the right spot. And so maybe you ignore it, right? Like, you're like, what is this thing? I don't really understand what's going on. And so the more you ignore it, the more urgent and sort of tyrannical the request becomes. And the idea was that if no one's paying attention to this thing, pretty soon it's going to start demanding that you move it, not just asking politely. And at the very end, you know, it's screaming at you like, you got to move me over to some other place, right? And so this was sort of a commentary, and a lot of people were misinterpreting what the point of it was, but I think it makes a good point about interaction. And so the artists themselves actually provided a little bit of a thought about this. They said, I don't mean to provide a commentary on the tyranny of technology. So he wasn't trying to say, you know, watch out, this is going to build Skynet. It was just a point of, hey, look, like, you can build these little pretty they're not that intelligent kinds of things in the real world. And it very quickly becomes this interaction. So it's not as if you build the technology and it just sits there in the corner. As soon as it's out there, there's somebody somewhere that's going to be interacting with it. And I think when it comes to teaming, when it comes to developing these kinds of advanced technologies, we really have to consider that interaction piece. And what's interesting about that example is that the government and the militaries around the world are struggling with exactly that interactive challenge. So in the control of unmanned vehicles, for instance, even when it's the simple case, and I would put simple in quotes because it's often very complex, we have a person that's trying to do a lot of different kinds of interactions with the technology available. So this may be one person flying one drone but they're still interacting with a lot of different components of the task. They're doing navigation, they're looking at the camera feeds, they're trying to assess the state of the vehicle and make sure it can continue to fly. They're trying to watch out for hazards and things like that. And so even in the sort of manual sense, it's pretty interactive. But of course, the goal with this technology has always been to transition it to where one person can actually control and oversee lots and lots of unmanned systems. And so whereas in the sort of early days, we can have a couple people, and often it was way more than just one or two, flying one aircraft that's unmanned somewhere and do a mission, what everyone really wants to move towards are lots of vehicles doing lots of different things with very little need for oversight. And of course, you can't have one person flying 20 or 30 or 100 or 250 different vehicles at the same time. You're going to need some type of machine or AI controller to do that. And so a lot of the challenge has been, if you design those controllers and they work, what role does the human really play in orchestrating those missions or orchestrating the activity of the vehicles or monitoring them for things that they may do inappropriately or challenges and disruptions? And so it's very similar in some ways to the combat vehicle task that Nancy just described to you, in that there's a lot of challenge in figuring out how are people going to interact with that kind of technology. And of course, the easy sort of push button solution here is, well, we'll just throw some fancy machine learning in here and there'll be no need for the human at all, which again is probably just incorrect. And it's very obvious that we need this automation and AI or autonomy or whatever other word you want to replace it. We need something controlling these other than people, or else the manpower issues just don't scale appropriately. If you want to control 250 vehicles, it's just not possible to field that many people to do that. And so we're going to need some kind of technology. But the problem is, even as far back as the 80s, we were identifying in the research literature in places like nuclear power plants, large scale complex systems, process control tasks, that automation and these kinds of technologies, the stuff that does things for you, can actually create quite a few problems. And this is a famous paper. I always encourage people to check it out. It's actually very short. It might be like 5 pages or something like that, called The Ironies of Automation. And in here, the author talks about how we often bring AI in to solve these challenges, like we don't have enough people, or they're not quick or smart enough to do certain things. And in the end, it actually does the opposite. So instead of solving the manpower issue, we now have to hire more people with more expertise to diagnose when the AI goes wrong. And you might say, well, that was, 1983, like who was alive back then? But the technology hasn't actually changed too much. And the evidence of that is that as recently as 2017, the retiring head of the National Transit Safety Board wrote a paper that essentially says, hey, remember all those ironic effects that people were worried about in the 1980s? Guess what? We didn't really solve any of them. And a key reason for this is that the rise of my field and the field that Nancy is a part of as well, this rise of human factors for this technology is still coming. It's still a small group of people who are trying to push these ideas, and it really hasn't made its way out into the world outside of perhaps aviation. And even then, you probably have heard in the news of various issues involved in automation or some type of AI in these complex systems that still creates problems for people. And so it's still not doing what we expect it to do. So the question is, if you want to use machine learning or you want to use these technologies, how on earth are you going to do it without creating these ironic effects, without causing more problems than you're solving? And so what we set out to do here was actually to use machine learning to build controllers for robots and in particular unmanned vehicles doing search tasks. So you might imagine that a pilot goes down in enemy territory and we know he's down there somewhere, but we really don't know where. We can plot out an area on the map and say, well, it's somewhere in here because we knew the speed and we know the kinds of wind and other things, but we don't really know where. We're going to go send a team of drones to find it out. And again, with this idea that we can't have individual people always controlling every little part of the task, we need some type of intelligence to do it. Now, it turns out that you can actually train machine learning controllers to search areas more effectively than human search patterns typically take. And there's some nice data on that in a lot of different forms. And so the idea was we're going to use machine learning to do these search tasks. But the problem is when the algorithms execute and move the vehicles around, are the humans actually going to trust it? And will they trust that there's something productive happening there? And so next in this talk, I'm going to describe the details of a simulated robotic search task that we used, details of a method called interactive machine learning, in which we actually have people and the machine learning sort of training as a team to improve the results of the search task. And this is a pretty novel method. It has been used in other areas and other tasks, but it really hasn't been used for any sort of behavior-based thing. So people aren't really using it to, say, train a robot to go and do a certain task. And finally, of course, because we're in chart and we care about the human, we have to measure sort of the human judgment and responses to this kind of technology. So we care about, for instance, whether people trust these kinds of controllers to do their jobs, whether or not people can identify that the plan or the behaviors that are happening for the search are good. And we're also kind of concerned that as we do this interactive machine learning, so as the human has a say in how the controllers are evolved, that it might actually degrade the performance. Because one of the great things about machine learning is if done properly, it often results in very good solutions to problems that humans aren't capable of creating by themselves. And so the worry was, well, if we add the human in here, is it going to destroy the performance? And of course, that was one measurement that we were going to take. And so I'm going to describe all of that shortly. So here's a little bit about the search task. We have here an example of a simulated environment bounded by this big blue box. And these dashed lines in the middle here are search areas. So it's almost as if we've said the pilot could be in one of these. You know, they could be anywhere in one of these things. And here we've given people a set of unmanned vehicles, and these are, of course, simulated. And they have some interesting properties, and the idea is that they're searching around in this space at a certain rate. And so the blue triangles here represent the current vehicle location. And as the vehicle moves along, it has sensors on board. And so where it is right now, it can sense very well. But that sensor coverage decays with time. And this is just kind of an idea that's present in any search and rescue operation, is that you may have searched there, but if you searched there an hour ago, you really don't know what's there now. And so we've tried to model that in this task. Now, again, these vehicles are moving around over time. And so if you've seen the last couple seconds of the search happening, you can tell where the vehicles have been. So you can see this decaying sensor coverage getting stronger and stronger until you actually arrive at the vehicle. And so using this as kind of a heuristic, you can tell, for example, how well the vehicles here are searching the space that you want to search. So the idea being, we actually need to train these vehicles to search most effectively within the spaces that we want them to, and not spend a bunch of time searching around, say, out here where we don't care what they find to some extent. Okay. So I'm going to outline a little bit of the experiment itself that we conducted. And of course, you're welcome to go and read the paper here. We have a paper in the Human Factors Journal. It has a very similar title to the talk, Dancing with Algorithms. You can find it pretty easily. If you have trouble with that, feel free to reach out and I will send you a copy myself. So in this experiment, we had 60 participants. They were all undergraduates in a psychology program, predominantly at another university. So people who, for example, aren't drone operators and don't come from military backgrounds. So we were very curious about how people without any of that would interact with this technology. And what we did is we asked them to interact with what was effectively an evolving plan to search these areas on the map. So we told them, the search coverage mattered. So I just described how, the vehicles have this sensor decay. And so, you want all that sensor coverage to be in the areas you want to search. And we said, okay, well, we're going to show you a number of different plans, a number of different ways that the vehicles might be traversing that area. And we want you to pick the one you like. So you pick the one that you think is good. And so it's essentially, selecting its preferred behaviors. Now, the interesting part here is this is essentially the interactive machine learning method. The algorithm is behind the scenes, developing the controllers and presenting an example to somebody. They say, I like this one or I don't like this one. When they like it, that particular set of behaviors is going to be put back into the machine learning and evolved further using their feedback as a sort of reward to the system. And all the ones that they said no to are pruned. So it's a way for people to have some say in the evolutionary process for a machine learning controller. So they view a number of these, and I'll get into that in a minute. And then following that interactive machine learning training, we actually assessed a number of different things. So first of all, as I mentioned before, we were concerned about performance. So we looked at how well the algorithms that were created with humans and the machine learning, and also just machine learning all by itself, actually performed in terms of searching the space, right? So performance is how well did the vehicles go over the space that we wanted them to. We also asked what kinds of behaviors would users actually prefer, and which ones would they choose if given the option? Would they choose the ones that they had helped train? Because that's our prediction. We believe that people interacting with this technology will build familiarity and trust, and may even build a preference towards it. Or would they prefer the purely no human involved machine learned behaviors because perhaps they would be more effective, or maybe they would look more like they expected them to be useful. Also, as anytime we deal with these kinds of technologies, we're interested in whether people trust it. And so we asked them whether or not they would trust these behaviors if implemented, and looked for differences between the two types, right? Would they trust the plans and the behaviors they had helped evolve, or would they trust the ones that had been evolved otherwise? And finally, we were really curious about, could they identify whether or not people had helped develop these behaviors or not? And this was based on some observations from my colleague, John Reeder, who was in a study in his dissertation days as a student that actually looked at people performing a driving task in a simulator, and they were using machine learning to mimic the behaviors of the drivers. And he was able to pick out the machine learned controller that had learned from his driving because he had a particular sort of behavior when he arrived at a stop sign before he would turn right. And so as he was watching the thing control the car in the simulator, he's like, that's me. That's the one you trained on me. So there's this idea that you might impart some traits or some characteristics by making these selections, right? So when you select, I like this type of search behavior, you are imparting in some way, some implicit preference or implicit behaviors that you might have. And so the idea is if you see those later, you might be able to recognize pretty well that, hey, that's the one that I helped train, or that maybe a person helped train versus one that it wasn't. And again, some of this is important because when you think about implementing these in a military environment, people have to have high trust and high confidence that the mission is going according to plan. If the robots drive off in a strange direction, or take odd turns or do odd things compared to what a human might do, there's a high likelihood that a commander will interrupt that mission, stop what's going on, which may actually degrade the quality of the outcome. So you can imagine stopping the search is just adding time to the time that the pilot is sitting down, potentially hurt or compromised by an enemy. So this is the basic gist here. So let's actually walk through each phase, and I'll show you what the participants saw. So one of the things we were doing here early on in this creation, so this is the interactive machine learning phase. A person is seeing a variety of different behaviors, right? So you can see there's a couple different ones, and these are happening in fairly real time. So when they're viewing these, the vehicles are actually moving around on the map. It's not a static picture as I'm showing you here. And the human selects the behavior that they like. So in this case, you can imagine someone saying, well, I kind of like this one. Maybe I don't like this vehicle over here, but these two are doing what I expect them to do, or something like that, right? And so this choice starts the machine learning algorithm working on this particular seed, and it goes and it works on that. And as it evolves further, a number of different evolutionary steps, it then creates more different option plans. And so you, as a participant, you see a number of these kinds of choices pop up on your screen over time. And so we actually manipulated the number of these that people got, as we were curious whether more choice would, encourage or increase the effects of things like trust. Because as you know, if you train with a team a little, you might have more trust in some strangers. But if you've been working with them for 10 years, your level of trust and familiarity with that group is much higher. So we manipulated that as part of this creation phase. And then, as I mentioned, these behaviors play out over a short time, and it ends up generating 2 controllers for each participant. And so we had 60 people, so we actually got 120 different controllers that allow robots to take action and search through the space according to that algorithm. So we actually generated quite a bit of material here. Now, using those controllers, we then moved people into a comparison phase in which we had them select the team to actually implement into the field. So we gave people 2 sort of sandbox representations and said, hey, this is the space you need to search. Here's what the vehicles are going to do. Choose one. Now, one thing they didn't know was that one of these plans was one of the interactive machine learning plans that had a human, and the other was not. And we randomized them between sides here. So if you always happen to choose the one on the left, it wasn't one category or the other. And we also held them constant for performance. So fitness is sort of the machine learning term, if you're unfamiliar with that. But what we wanted to avoid was people making a decision that was clearly based on how well the vehicles were doing here, right? So if you watch them and the vehicles are doing terribly in one and awesome in the other, you might make your choice based on that rather than on, say, more subtle things like the behavior of the vehicles. Do you like the fact that these are going in straight lines? Or do you like the fact that maybe in the other one they could be going in a circle or doing something different? After people made these selections, so they're effectively choosing one or the other, even though they may not necessarily know which one's which, they give a trust rating from 0 to 100. 100 being, I trust this 100% completely, and 0 being I don't trust it at all. And of course, as you might be thinking to yourself, well, if I choose one, the chances that I would trust it are much higher maybe than normal. And that was indeed the case, and I'll show you those results in a second. And then finally, again, because we were curious whether people could actually recognize these kinds of things, we just presented single plans or like a single set of behaviors here and asked them to actually try to judge, try to categorize. Which kind of behavior is this? Is this one that the human helped evolve? Or is it one that the computer did by itself? And we did this over 80 trials as well. Again, they don't realize, but we did 50% one, 50% of the other, and they're all jumbled up in here. So, it wasn't as if like someone saw one type of thing all in a row and then another type of thing. Unlike some of the other parts of the experiment, we actually gave people feedback on their answer. And the idea here was you may start this task unable to differentiate between the 2 types. But if there is some way to differentiate, if I give you feedback on you being correctly identifying it or incorrectly identifying it, you might learn what the difference is. And that's a really interesting concept too, because again, if you're a commander somewhere and you're watching these plays happen, what we really want is people being able to differentiate, things that might be going well versus things that might not be. And so what kinds of characteristics in the behaviors might be noticeable and therefore trainable. We could actually give this kind of task to somebody who hasn't had any other hand in the generation or in the training, and maybe we could teach them what to look for and what to allow or not allow. And so we can talk about how people did on each one of these things. So again, I want to start with the performance data out of this because I think it's usually the pressing question people have. Did the people screw it up? And that was not the case. So I mentioned we had these 2 categories of high interaction, so people making lots of choices during the interactive machine learning phase. So lots of inputs and then the algorithm is sort of iterating on it. And a case in which we had far less. And so, of course, one of the assumptions was that with more interaction, we might get higher performance and higher trust and higher preference. And at least in the performance data, you can see here on the red line, these interactions with people. So these are all the performance in the best cases of interactive machine learning. So people are interacting with the algorithm, and this is how the algorithm performs. We see that it's actually very similar to the black line, which is machine learning completely absent a human. So again, we were concerned that adding people might actually, degrade the fitness, degrade the performance, degrade the search ability of the algorithm, but we don't really see any evidence for that. And indeed, these aren't different. These are very similar in terms of performance. So as long as we're taking good cases, so a participant that was paying attention and really trying to make the algorithm improve, we generally get improved results. Now, one thing I will note, it's not as steady an improvement, and occasionally you get these little gaps in fitness. And so there are issues, but again, at the end, over time, these are effectively very similar performances. So that's pretty cool. It suggests this method might have some utility behind it. Next, we looked at people's preference. So you'll remember that we gave people these options and said, choose the one that you want to implement. One was IML and the other was only machine learning by itself, and they didn't know which was which. And it turns out that in general, people are selecting, in other words, they preferred this interactive machine learned trained behaviors about 66% of the time. So this is a significant finding. Though the amount of interaction people had, and you'll remember there was that high interaction or low interaction condition, we expected the high interaction would improve this, but we found no difference. So it turns out that at least at the levels of interaction we were doing in this experiment, we really didn't have the influence in this that we thought we might. Also, the interactive machine learning behaviors were trusted more than machine learning behaviors when they were selected. And this is not a huge difference in terms of trust data. 0 to 100 and a 5% difference here. It was statistically significant, and the effect size is moderate. But again, as I pointed out before, if you're choosing to implement one of these, the chance that you trust the thing that you choose is fairly good. And so you might suspect that, well, we have 60% or 66% of the time people are choosing this one, so they're choosing it more, so they might trust it a little bit more. But if you are choosing the other one, there's a good chance you trust it quite a bit as well. So this difference is kind of nice to see, but I suspect it would be far greater if we made one of these plans bad, right? So that's sort of an area for future research. Here, we're only presenting people good plans with the equivalent performance, but what we should really be doing is also comparing it to when things go poorly. So the bottom line here is they select the interactive behaviors more often, and when they select them, they trust them more than they do the machine learned behaviors by themselves, which is a nice fit to our prediction. Next, let's talk a little bit about the recognition of the type. Turns out that we can actually have participants recognize which type of unmanned vehicle behaviors it is. So were they trained with the interactive machine learning or not? And showing that this is possible is very nice. So first of all, it's better than chance, so they can identify these things better than chance. And when we break the data down over the number of trials, and here we've used quartiles, but you'll recall there were 80 trials, and so we've simply split this into the first 20 trials in quartile 1, the second 20 trials, so trials 21 through 40, and so forth. And so what you can see is they were about 76% accurate at identification overall, but this identity accuracy improved over time. So right off the bat, they're doing better than chance, but by the end, they're at about 80%. There is some variance here, which is to be expected, but with a fairly large sample and a large number of tests here, we're fairly confident that people are accurately identifying these, and that by providing feedback, we can actually improve their accuracy. So this may not be the upper bound of people being able to recognize which type of behavior is what. And that's very interesting to consider, but it becomes even more interesting when you think about how people might be able to recognize these different types of behaviors. So in this case, we ask people in a sort of set of questions at the very end of the experiment. So at this point, a participant has participated in the interactive machine learning development stages. So they've made choices and the algorithms evolve and they make more choices. They did the comparison phase where they said, I want to implement this one. And they did the recognition phase where they said, I think this is an interactive plan, or I think this didn't have a human involved it, and got feedback. At the end of this, we said, was there anything that you were looking at or using to help you identify which plan was which? So any sort of subjective impressions of what you thought one type of outcome had or didn't. And so when we looked at this data, this is all qualitative responses. So people are just writing sentences describing what they saw or what they thought was useful to look at. We did find some themes. So one of the biggest ones was simply the behavior of the unmanned vehicles themselves. This included things like how fast they were moving, because vehicles can obviously vary in speed. The type of movement. So were they really moving in a trajectory? Were they making lots of turns? And of course, the actual coverage provided by the vehicle. So was the vehicle staying within the boundaries and really providing good sensor coverage over the course of the task? And this is contrasted with times in which maybe that behavior is more random or sporadic, whether the vehicles may have sort of spun in a circle, which again, these are the kinds of purely machine learned outputs that can occur when you give feedback for sensor coverage. So sometimes we've seen machine learning algorithms essentially learn that you can get decent sensor coverage by traveling in a circle so that you're coming back on yourself as the sensor decays, beyond a certain point of effectiveness. But the problem with that is, from the human perspective, that's not searching the space effectively. And so there might have to be some tweaks to that. And so people were making feedback choices that said, I don't like when these things spin in a circle. And so most of the interactive machine learning plans don't really have that kind of behavior. And then finally, people did report that sometimes they simply recognize, just as my friend had in his driving experiment, hey, I've seen that behavior before, that's one I selected. So there was some evidence of that. And so I just want to highlight a couple of these. So again, people noticed pauses and vehicles stopping and used this to discriminate between the types of tasks. So machine learned plans tend to have more of those kinds of weird, sort of spurious behaviors, and the interactive ones did not. And this makes perfect sense. If you've ever trained a group of people, much like you would train these algorithms, when you see weird things, you call them out, right? You say, hey, that's not how you do this. Why did you stop and stare at this thing over there? You're supposed to be paying attention to the goalie or whatever it is, using kind of a sports metaphor, right? So it's unlikely that as people train with these algorithms, that these weird things survive over the evolution of the behaviors. And so this becomes an interesting point to talk about. But it becomes even more interesting when you look at across 60 people, we got 24 different statements that noticed that these pure machine learned vehicles do this kind of thing. They stop or they move very little. 10 people characterized that the human evolved vehicles tended to have consistent movement, and often within or towards the goal spaces. In other words, movement that made sense to the goal. This is actually a direct quote from one of the participants. Even though there were 3 people that sort of disagreed with that. So it's kind of interesting. Again, we're learning that what people sort of anchor on to say this is good or this is bad tends to be these little behavior characteristics. Now, it's possible that by understanding the characteristics that people like and have a preference for, we can start engineering even the purely machine learned task with those kind of properties, and therefore make them more acceptable to people. So one of the challenges again was that these machine learned algorithms tend to search these spaces very well, even though it looks crazy. So can we make it look less crazy, but still search the space well? And this, of course, is going to be a subject of of ongoing research. So some of the things I'd like to tie up this talk with are that, hearkening back to Nancy's discussion about human AI robot teaming principles, the interactive machine learning method doesn't attempt to replicate humans. So I got a lot of commentary and interaction when we were developing this project that was, well, if you're going to use machine learning and people know how to search these spaces, and sometimes they may know how to do it better or avoid issues, more than a machine, why don't you just use machine learning to, create a human-like controller, right? And of course you could do that. And in fact, a lot of classification algorithms are basically bootstrapped by human experts. So there's, funny examples of people doing classification of images, for example, where the AI is actually fairly dumb and doesn't get it correct. But when you farm it out to a large group of people, they get it right most of the time. And so you can sort of get the algorithm to understand what the differences are by feeding it data. And it takes a extremely large amount of data. So one of the reasons we chose not to do that was that it takes an extremely large amount of data, which is very hard to do in military settings. So if you go and you work for Google or Facebook or whatever, you can actually do really fancy machine learning stuff because they have an enormous ability to collect data on things like categorization tasks. In the military, a lot of that data is going to be sort of clustered away. Maybe it's classified, maybe it's a mixture of classifications, but whatever reason, it's very hard to pull it all into one database and do something with it. And so that was yet another reason why typical machine learning methods in this area don't really address the problem. The other is that most machine learning methods have almost no focus on the human's interaction with it. And all of the human components are addressed sort of as an afterthought. And so, you can see some evidence for this in a lot of the advancing technologies and drone controllers, because the drones themselves have gotten really, really good. They're good at obstacle avoidance. They're good at plotting paths and traversing them. They're good at formation controls. There's lots of stuff that's been improved by technology. But you got to remember, at the end of the day, the people who are going to interact with these have a mission in mind. They have certain expectancies. They have things that they want to see and things that they don't. And usually the controllers and the technology used to develop these drones don't take any of that into account. And it's not really their fault. It's very difficult to determine what those kinds of properties are. And you've seen in this project that figuring out what it is that people anchor on, what is it that they think is good, what is it that they don't like, can be very challenging. And in fact, there's some evidence that people don't even know what those are. So if I had sat down in this study and say, tell me what you want to see in the drone, tell me what you like and what you don't like, we may not really want to trust that kind of evidence. It can be useful, but it's certainly not the only thing to pay attention to. And there are a lot of these sort of implicit or sort of under the surface properties that people judge the technology on. So the cool thing about interactive machine learning is that we have people interacting with the technology as it evolves, which is much more similar to how we train with other people, right? It's very rare that you'll enter a training environment and not interact with the rest of the team, and which is essentially how, a machine learning algorithm all by itself is sort of violating that teaming idea. And so the interactive component of this is really bringing us closer to better trust and understanding by more interaction and more training with each other. So I want to just provide a quick take home here. This appears to be a really promising method to improve human AI robot teaming. It's still sort of in its infancy, and of course, we've been using it in these very basic simulations, but we are going to expand that. And since it looks like I have a few minutes here, I'll probably show you a video of something I'm pretty excited about. But at the end of the day, that interaction piece, I think, plays a big role. So it's shown in this experiment, at least, to improve trust and people's preferences for search and rescue stuff. And I think it could be useful for other things. But the real scientific question that remains is, like, why does that work? We have some theories about what it was that made those particular behaviors better for people and more trusted, more preferred, but we're not really sure why. So we need to determine what drives that kind of improvement, right? Is it the training? So is it the part where they're selecting a plan and allowing that plan to evolve? You know, we don't really have evidence for that at the moment, right? Because we had a condition in which people essentially engaged in more of those training periods, and it really didn't affect their data very much in terms of the trust or the preference or what they were noticing. Has it something to do with what characteristics you impart into the controller? And if so, is it just going to be unique to you? So like if I train my cool robots up and I trust them and they're awesome for me, if I hand them over to you for you to sort of watch over on a mission, is it going to work? Are you going to say, oh yeah, this is fine, I understand what they're doing, we agree, we have similar things? Or have I just created yet another sort of specific tool that works for me, but once you see it, it looks weird and crazy and you don't like it? And so those are important questions when you think about how the military implements this technology, because it's very unlikely that people will have personalized you know, controllers for these types of missions. It's much more likely that these missions will be shared across a lot of different people doing both coordination tasks, so you know, watching where the robots go and then coordinating where other people go, and of course supervision and command and control. So you have to have a commander looking at what's happening in the field and saying this is good or this isn't, we need to do that or we don't need to do that. And that person may not have been the one that trained the team of robots. And so we have some work to do in thinking about how to solve these problems. Now, I have just another one little couple minutes worth of a video, but I figure I'd stop here because I'd rather have questions and discussion at the end of this than go directly to the video. But if we're low on time and space here, I do have a video on the slide after this that I'm happy to play. It's just 2 or 3 minutes. So with that, I'm happy just to open up to questions here.
So, Robert, I have a comment.
Sure.
I think it's really, really cool how your findings sort of reinforce the idea that humans and AI need to team together and train together, that it's their interactions that are important and that you shouldn't replicate AI in humans. Replicate humans in AI, rather.
Yeah, I think, you know, the challenge with these technologies is always that we can, so like machine learning in medicine, for example, right? They look at doctors diagnosing patients and they go, oh, well, like doctors make mistakes, so we better train up a machine learning algorithm. Not only might it diagnose them more effectively because it's always going to take into consideration the full range of data. You know, we know humans are limited in the amount of information they can process at any given time. But they might also observe patterns that are unobservable, or just, you know, too many levels of interaction. And the best case for this I can talk about is that machine learning classifiers for suicide prediction are actually incredibly accurate, to the point now where there are groups of people pushing for their use in clinical practice, and some I think kind of fringe discussions about whether or not clinicians can make other diagnoses, because these models are now in the range of 90 to 95% accurate at predicting who will make a suicide attempt based on case notes and some other things. Now, what's incredible about that is the clinician rates of that are barely above chance in the best cases. So this is a gap between what the AI can predict and what the practitioners can predict that's really hard to explain. Like, what is it about? Like, what are the clinicians missing, you know? And so I think replacing people would have been a terrible idea for that. in some ways, because you need the clinician to be the person that interacts with a client, but at the same time, the argument that one thing is so much better and outperforming it at something like suicide prediction, it's very easy for people to come in from the AI world and say, well, these stupid clinicians are killing people. Like that's the kind of leap in logic that gets made. And so you have to have a strong case for why, most likely the best accuracy is going to come from this algorithm in combination with expert clinicians and expert practitioners, because even the algorithm is limited in what it can see.
And really, this kind of tight coupling of humans and AI goes along the same lines as the centaur concept, that you have this human-machine pairing that's superior to what either could do alone.
Yes, there's a lot of synergistic kinds of things. Certainly in this experiment, we were kind of interested in making a kind of a control condition in which people are just allowed to move vehicles around on their own, but we knew how much worse they would do in that case. So the sponsors weren't even interested in entertaining the thought, because the military has largely concluded that people can't do this, and we need to work on the technology and the interaction more than we do training individuals and things like that. So there are certainly elements still working and trying to improve that sort of trying to get unmanned control down to one, one person, one vehicle. Surprisingly, that's still a hard thing to achieve in these spaces. Well, I don't see other questions, and I really do like this this video. So now that we have 10 minutes, I'll just narrate and talk through this video real quick. It's pretty short, but the idea was that in our previous simulation, we had basic maps and basic searches, but people have a lot more interest in drones for other things besides search and rescue. And one of those things is thinking about drone versus drone combat. And so one of the things that's really interesting is thinking about how those drone strategies may need to be created. And so, of course, the military has lots of tactics and training for manned combat. And so you watch Top Gun and you understand that the pilots have maneuvers and tactics and things like that. And it's a lot harder when you start thinking about huge drone fleets fighting each other. So 250 drones at a time, taking on 250 other drones. And so, of course, one of the things that you'd want to do is try to simulate this, and that's effectively what this particular platform allows you to do. What's also interesting is that, and this is where this part comes in, the simulation allows you to evolve a strategy for winning the battle. So it's no longer just a person comes up with some tactic or some hand-designed function that says, well, I want this many vehicles to survive and I want them to do this or that or the other. You actually allow those parameters to be freely evolved by the machine learning, and over time, you get some very different behaviors. And so the point here is, these are in some cases going to be constantly evolving, constantly changing tactics, which means from the human perspective, in this case versus the one you just saw a second ago, that blue fleet did something completely different. So imagine being the commander in charge of that fight and seeing the vehicles doing something strange to you. What are you going to do? You going to let them do it? Like, maybe it won't work. You don't have any confidence in what's going to happen. But the cool thing is that these are very advanced simulation capabilities compared to what we were using in our task. And so the question is, could we do the same type of experiment or do the same type of interactive machine learning to improve these strategies as well? So it'd be one thing if, much like with the search performance, if machine learning wins these fights more often, and in this case, in that work, it was doing really well, kind of bootstrapping itself, much like other AI applications you've heard of, like AlphaGo and things like that. But again, from the operator perspective, when you see your big team of vehicles that you don't want to be lost start engaging, you have to know to some extent that this is a good plan. And if it's the machine learning that's developing those plans, then you're going to be pretty much in the dark about what could or couldn't happen here. Not to mention, this is devoid of things like collateral damage and things like that the military is very sensitive about, and rightly so. And so, when you let loose this kind of technology on the world, you really want to have more confidence that it's not going to cause problems.
Any questions? You guys are quiet.
It reminds me of teaching this semester. Well, for those of you who are here or are coming later to look at the recording, seriously, please reach out to either myself or Nancy on these things. We are really very collaborative, and the center is growing and we're maturing, and it's way more than just us doing this work. So although we happen to be the people talking and showing what we're doing, there are quite a few other groups doing stuff as well. And so if you're like, well, I'm not in human systems engineering, how am I going to do anything? There are plenty of people in the other disciplines, computer science and other forms of engineering, who are helping us and working with us on various things. So talk to your advisor, talk to your professors, find out how, maybe you can get them interested too. Oftentimes the students come to me with a cool idea, that engages me more than if I think of it myself, because now I know there's someone to help me. So really, don't hold back. Use this innovation quarter to inspire you to do things like that. That's where a lot of the innovation comes from, is sort of transdisciplinary interaction.
Can I ask you a quick question?
Absolutely.
Have you ever tried training drones or kind of swarms of drones or devices on animal behaviors instead of humans?
So to kind of mimic them, you mean?
Yeah, like for instance, if you wanted to get a drone swarm to act in a more natural or better way, you could train them on like a bee swarm or something when they attack a potential predator or something. Is there stuff out there like that instead of using humans to train?
Yeah, absolutely. So you might be familiar, but if you're not, we have a kind of world-renowned researcher doing exactly that here at ASU. Her name is Spring Berman. She's actually part of CHART as well. And her research, or at least part of it, is very much about looking at biology as an inspiration for how to control large swarms of drones. And I think, I can't remember, I think she was mostly interested in ants for a while, but I'm sure there are lots of different biological models for those things. So I would definitely check that out and certainly reach out to her if you're interested in that stuff. I would say though that, again, the challenge is that humans don't know what ants do. You might be familiar with the idea that an ant lays a pheromone track for other ants to follow. And then if you put that model into drone control, then it's a really effective way to get drones to move around, but a human doesn't necessarily understand what's good about that or if it makes sense to the mission. And so they can be useful metaphors for control, but not necessarily the command element. I want to know, is that vehicle going to help me find the pilot or not? And vehicles laying pheromone tracks is like, yeah, okay, anyway, tell me if it's effective or not. Tell me if it's going to get there on time, things like that. So it's challenging to integrate the two, but I think there are probably upcoming opportunities to attempt that.
And I might add, I'm working on a DARPA ISAT study that is looking at human animal teaming as an analog for human AI teaming. And so we're looking at things like, how does a dog understand the intent of the handler? How does the dog and the handler communicate? How do they share situation awareness or share mental models? And so we think that we can get a lot from that kind of biological inspiration in order to make AI that's a good teammate.
Yeah, great question though.
Any other questions? We have 3 minutes left, or we can return them to you.
Yeah, so Pauline just linked to an article, I think about spring and some of her work. So Reese, if you want to check that out.
That's in the chat. Are we saving the chat, Pauline?
Yes.
You can put the chat on the canvas.
Yeah, we can do that.
Okay. And I want to thank Pauline for helping us coordinate all of this too. Thank you very much.
Yes, absolutely. And thanks to everyone who came. I think these innovation quarters are an interesting idea, and it's fun to give sort of short versions of things that normally maybe we'd have to spend a whole semester to get to.
Yeah. I also want to thank the students that are, some of them on the Zoom, who helped put together the videos that I showed. Okay.
Okay.
Well, thank you all for attending. It's been great.
Yep. Thanks again, and reach out anytime.